There is a version of the future that cosmologists have carried with them, almost like a quiet certainty, for nearly 3 decades. In it, everything ends slowly. Galaxies drift apart like ships losing sight of one another on an ocean with no horizon. Stars exhaust their fuel, the ones burning brightest coming first, the smallest cooling last, until even the red dwarfs wink out across timescales too vast for language to hold. Black holes persist longer than anything else, but they too eventually surrender, radiating away their mass in a process so gradual that Hawking himself called it evaporation. And then, nothing. Not darkness in the way we picture it, full and dramatic and close. Something far stranger. An infinite, featureless expanse at a temperature so close to absolute zero that the distinction barely matters. No motion, no heat, no structure. The universe dissolves not into chaos, but into the most profound stillness imaginable. Cosmologists call it the Big Freeze, and until very recently, it was the most defensible answer to the oldest question: how does everything end? What has begun to change that answer, quietly, through the patient accumulation of evidence, is one of the most consequential stories in contemporary science. It begins with a faint signal in starlight. It runs through some of the most sophisticated machinery ever built to study the sky, and it lands us at a possibility that, if confirmed, would require us to rethink not just the fate of the universe, but the architecture of our best theory of cosmic evolution. The story begins with dark energy, and to understand why its behavior matters so much, it helps to understand how we discovered it in the first place. It is 1998. 2 independent teams of astronomers are studying some of the most violent events in the observable universe, Type A supernovae, the thermonuclear deaths of white dwarf stars in binary systems. These explosions are useful to cosmologists for a specific reason. Because white dwarfs detonate in roughly the same way, accumulating mass from a companion star until they cross a critical threshold and ignite, they produce a characteristic brightness. The peak luminosity of a Type A supernova is, to a good approximation, a known quantity. That makes it what astronomers call a standard candle. Compare how bright it actually is to how dim it appears from Earth, and you can calculate how far away it is. Factor in the redshift of its light, the stretching of wavelengths as the universe expands, and you can determine how fast space itself was expanding when that light was emitted. It is, in principle, a clean measurement. In practice, it produced a result that nobody expected. The supernovae were dimmer than they should have been. Not by an amount attributable to dust, or instrumental error, or miscalibration. Dimmer in a way that implied they were simply farther away than the models predicted. The teams, led by Saul Perlmutter, Brian Schmidt, and Adam Race, had to confront a conclusion that strained credulity. The expansion of the universe was not decelerating under gravity's pull. It was accelerating. Something was pushing galaxies apart faster and faster, and that something left no trace in any existing theory. The 3 astronomers were awarded the Nobel Prize in Physics in 2011. The force they had, in effect, discovered was given a name: dark energy, and slotted into the most widely used framework in cosmology, the lambda CDM model. Lambda, a Greek letter, represents what Einstein had once called the cosmological constant, a parameter encoding the energy density of empty space. The name implies what the model assumes: lambda doesn't change. Dark energy is a fixed property of the vacuum itself, constant across time, constant across space. It is a deceptively simple assumption, and for 25 years, it held. Before continuing, it is worth pausing on the scale of what that model contains. Under lambda CDM, the universe is composed of roughly 5% ordinary matter, the atoms, molecules, stars, planets, and everything we have ever touched, studied, or named. Dark matter, which interacts gravitationally but not electromagnetically, which we cannot see, only infer, accounts for approximately 27%. And dark energy, the cosmological constant, the thing we understand least and cannot measure directly, constitutes approximately 68% of the total energy content of the observable universe. 68%, the dominant constituent of everything that exists. And the only reason we believe it's there at all is that without it, the expansion of the universe doesn't make sense. This is not a footnote. This is the foundation. And the crucial load-bearing assumption beneath that foundation is that dark energy is constant, that lambda doesn't evolve, doesn't weaken, doesn't change its behavior over billions of years. The big freeze is only inevitable if that assumption holds. Remove it, and the future of the universe becomes, once again, an open question. In 2024, the Dark Energy Survey released what was then the largest single survey supernova dataset ever compiled. More than 1,500 stellar deaths cataloged and analyzed. The initial results appeared consistent with the standard model. Dark energy looked constant. Lambda seemed stable. But data does not exist in isolation. When the survey's results were combined with other independent measurements, readings from the cosmic microwave background, older galaxy surveys, something resisted easy reconciliation. The datasets didn't contradict one another exactly, but they didn't agree cleanly either. There was a tension, a residue of inconsistency that the model couldn't absorb without strain. It was starting to look as though dark energy might not be constant after all, that lambda might, in some sense, be alive, varying across cosmic time in ways the standard model did not anticipate and could not accommodate. This was not a discovery, not yet, but it was a signal, and signals in cosmology require instruments built to resolve them. The Dark Energy Spectroscopic Instrument, DESI, sits atop the Kitt Peak National Observatory in Arizona, mounted on the 4-meter Male telescope. Its purpose is precise and ambitious: to chart the optical spectra of tens of millions of galaxies and quasars across billions of years of cosmic history, constructing a 3-dimensional map of the universe in sufficient detail to test whether dark energy is constant. The instrument can capture light from 5,000 galaxies simultaneously. It is measuring the position and recession velocity of some 40 million galaxies, reconstructing the expansion history of the universe over the past 11 billion years. The collaboration spans more than 900 researchers at more than 70 institutions across multiple continents. By the standards of scientific infrastructure, it is extraordinary. What DESI measures, specifically, are Baryon acoustic oscillations, BAOs. These are not phenomena most people have heard of, but they carry enormous scientific weight. In the first moments after the Big Bang, the young universe was an intensely hot plasma of particles and radiation. Sound waves, pressure waves, propagated through this primordial medium. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, roughly 380,000 years after the Big Bang, the plasma froze. The sound waves stopped. Their imprint remained. Those frozen ripples, fossilized echoes of the early universe's acoustic activity, left a faint but measurable signature in the distribution of matter. They appear as a preferred clustering scale among galaxies, a kind of statistical ruler embedded in the cosmic web. Because the physical size of this ruler is known from the early universe physics, measuring how large it appears at different distances allows astronomers to trace how the universe was expanding at different moments in its history. It is, in essence, a technique for reading the universe's expansion history directly from the arrangement of galaxies. In 2025, DESI released its first major datasets, Results from the first 3 years of a 5-year survey, built from observations of nearly 15 million galaxies. The resulting 3-dimensional map of the universe is the largest ever constructed. Visualize it. Earth at the center, every point of light an entire galaxy, some containing 200 or 300 billion stars. The whole structure stretching back more than 10 billion light-years, densely woven into filaments, sheets, and voids. The scale is not one that intuition can genuinely grasp. It must simply be accepted. From this map, using Baryon acoustic oscillations as the measuring tool, DESI's researchers extracted the expansion history of the universe with unprecedented precision. They then combined this data with independent measurements: the cosmic microwave background, supernova redshifts, weak gravitational lensing, the subtle warping of distant light by the gravitational influence of matter along the line of sight. Each dataset contributes different information. Together, they triangulate the behavior of dark energy across cosmic time. The result added weight, significant weight, to what the Dark Energy Survey had hinted at the year before. Dark energy does not appear to be constant. Its influence appears to be weakening. The best current estimate suggests that the push exerted by dark energy may have diminished by roughly 10% over the last 4.5 billion years. The universe is still expanding. The acceleration has not stopped, but it may be easing. Imagine a foot still on the accelerator, not pressing down harder, but gradually, almost imperceptibly lifting. The car is still speeding up, but the rate of that acceleration is declining. If this is accurate, lambda is not a constant. It varies. And if it varies, the standard model of cosmology, lambda CDM, the framework that has organized our understanding of the universe's past and future for more than 2 decades, is incomplete. The implications of an evolving dark energy are not only cosmological, they are structural. If dark energy changes over time, then the mathematical framework used to describe it must be replaced or substantially revised. The cosmological constant, as Einstein conceived it, cannot vary. It is, by definition, constant. An evolving dark energy requires what physicists call a dynamical dark energy model. Something more complex, with additional parameters, possibly new fields or forces not yet represented in any existing theory. General relativity itself may require modification at cosmological scales. The equations that describe gravity across the observable universe may need to be extended, amended, made richer. Particle physics may need to accommodate new degrees of freedom, additional scalar fields, novel dynamics in the vacuum of space to explain why the energy density of empty space is not what we assumed. And the fate of the universe changes. If dark energy continues to weaken, not merely declining but eventually crossing zero and becoming negative, then the universe's expansion would decelerate, stop, and reverse. Gravity, now unopposed by the outward push that has been driving galaxies apart for billions of years, would begin to reassert itself at the largest scales. The cosmic web would start to contract. Galaxies, which have spent billions of years drifting apart, would begin drifting back together. Over timescales that dwarf the current age of the universe, the convergence would accelerate. Everything that the Big Bang separated, every galaxy, every star, every atom, would approach a single point. This is what cosmologists call the Big Crunch, the inverse of the Big Bang. Not an ending in stillness, but an ending in intensity. All the energy that has ever existed compressed back into a singularity. Whether something persists afterward, whether the equations allow for a bounce, a rebirth, a new universe emerging from the collapse, that remains unknown. The Big Freeze and the Big Crunch are not merely different endings, they are different universes, different physical realities, and which one awaits us depends on whether dark energy is what we assumed it to be. Science is not decided by suggestion. Evidence must cross thresholds. Physicists measure confidence in units called sigma, derived from standard deviation. a statistical measure of how far a result sits from what random chance alone would produce. At 2 sigma, there is roughly a 5% probability the result is a statistical fluctuation. At 3 sigma, that probability drops below 0.3%. At 5 sigma, the conventional gold standard for claiming a new discovery, the probability of a chance result falls to about 1 in 1.7 million. DESI's data alone currently sits just above 2 sigma on the question of evolving dark energy. Interesting, suggestive, not sufficient. When DESI's results are combined with complementary datasets, cosmic microwave background measurements, supernova surveys, gravitational lensing, the confidence climbs. In some combinations, it brushes past 3 sigma, reaching toward 4.2 sigma. That is strong evidence. It is not a discovery. The history of physics counsels patience here. In 2011, researchers at the Gran Sasso Laboratory in Italy measured neutrinos that appeared to arrive slightly earlier than they should have, implying, if taken at face value, that the particles had traveled faster than light. The reported confidence was 6 sigma, more than a standard discovery threshold. The result was real and reproducible within their own system. It made headlines worldwide. It was later traced to a faulty fiber optic cable and a clock synchronization error. The physics had not broken. The equipment had. The lesson is not that high sigma results are untrustworthy. It is that systematic errors that are not random, that consistently push results in one direction, can survive statistical scrutiny. Until those systematics are understood and ruled out, caution is warranted. The DESI Collaboration is aware of this. The survey has 2 more years to run. By its completion, the dataset will encompass roughly 50 million galaxies and quasars. The statistical precision will improve substantially. DESI will not be operating alone. The European Space Agency's Euclid mission, launched in 2023, is designed to map the geometry of the dark universe across a larger volume of space and at higher redshifts than any previous survey. It will extend the measurement of Baryon acoustic oscillations and weak gravitational lensing to scales and depths that complement DESI's observations. NASA's Nancy Grace Roman Space Telescope, when operational, will contribute a wide-field infrared survey capable of probing the universe's expansion history through multiple independent methods. The Vera C. Rubin Observatory in Chile, with its 8.4-meter mirror and unprecedented survey speed, will catalog millions of supernovae, generating the statistical depth needed to push confidence in dark energy measurements toward and potentially past the 5 sigma threshold. These instruments will not all agree immediately. Science rarely proceeds in clean, simultaneous confirmation. There will be tensions, unexpected discrepancies, results that require reanalysis. That is not a failure of the process. It is the process. What is certain is that the next decade will resolve or substantially advance the question that DESI has placed at the center of cosmology. Is dark energy constant, or does it change? If the answer is the latter, if what DESI is measuring is confirmed, the consequences will be felt across physics, not only in cosmology, but in fundamental theories of space, time, gravity, and the vacuum. New models will be proposed. Some will be ruled out quickly. Others will survive long enough to be tested against the next generation of data. The standard model of cosmology, lambda CDM, built on decades of observational success and mathematical consistency, will not be discarded. It will be extended, revised, pushed into new territory. Science does not often throw away working frameworks. It expands them. What DESI has given us at this moment is not an answer. It is something almost more valuable, a well-posed question, accompanied by evidence that demands attention. For 25 years, the fate of the universe appeared settled. The Big Freeze, cold, vast, still, waited at the end of an expanding universe driven by an unchanging dark energy. It was not a comfortable picture, but it was a coherent one, grounded in observation, supported by the most successful cosmological model ever constructed. Now that picture has developed a crack. Small, perhaps, possibly a systematic artifact that will disappear when the data improves, but possibly real, possibly the first glimpse of something the standard model cannot hold. If dark energy is weakening, if the foot is lifting from the accelerator, then the universe's future is not written. The big freeze remains possible. The big crunch becomes plausible. And between those two endings lies an entire landscape of theoretical possibilities that physicists are only beginning to map. Somewhere in the light of 15 million galaxies, carefully measured and cross-referenced and triangulated against every independent dataset astronomers could bring to bear, there is a signal. It says that dark energy may not be what we assumed. It says the universe may be behaving differently than our best theory predicts. It says, quietly and without fanfare, that we may not yet know how everything ends. That is not cause for alarm. It is cause for the particular kind of attention that science, at its best, knows how to pay. Patient, methodical, and open to being surprised. The instruments are running. The data is accumulating. The question is sharper than it has ever been. We wait.